in this lesson we are looking at resistance and resistivity. Firstly, resistance is a measure of the retardation or the restriction experienced by the charge flowing through an object. And we use the unit of ohms, so it comes from the Greek letter omega. That is the symbol that we use for resistance. So ohms, so it's the limitation through a circuit or an object. Just like if we go back to our garden hose analogy, if current is how fast the water is flowing, it's the rate of flow. Resistance is like putting a restrictor in the pipe. It's like crimping the pipe, making it smaller at a certain point. That then restricts the flow. So the flow will build up and it'll have to work harder to get through it. And that is how resistance works. A good conductor is just something that has a very low resistance. So something that has a really large garden hose, for example, has a very low resistance because the charge can easily flow through it. So when we've talked about resistors and insulators, electrically, we're just talking about that resistance. So it won't restrict the flow much for a good conductor, whereas an insulator has a very high resistance. So very little flow, if any, can travel through the object. And the relationship between potential difference, which we've seen now as V, the current I, and the resistance is given by Ohm's law. And we'll talk about Ohm's law today, which is very important. So it's the I equals V on R, or V equals IR equation that you see quite often. This is a resistor color code chart. So for a standard resistor in an electrical circuit, they kind of look a bit like this. It's like a little ceramic tube with metal ends on it, which are your wires for connecting, and they have all these colored bands. So we'll use these a lot during the lesson and in future experiments when we build some circuits. But this is a really good guide to help you figure out what is the size of the resistor. So for example, the first band gives you the first digit of the number, the second band gives you the second digit, and you can have more bands. So if your resistor has more bands than this, there is sometimes a third and a fourth, but otherwise then you have a multiplier and a tolerance. So for example, if we look at this resistor here, we've got a green, which is a 5, then we've got a 6, and we multiply it by 100. So we've got 56 times 100, so we've got a 5,600 ohm resistor, or a 5.6 kilo ohm resistor, because kilo is 1,000, so you sometimes see it like that, 5.6 k ohms. And then the tolerance here is a silver, which is a 10%. So you can think of that as like a precision of the resistor. So it's a 56 k ohm resistor, give or take 10%. That's sort of the buffer. So if we need to know something very, very specific and we needed a very exact resistance, we could probably get a better resistor. We can get a gold band resistor, which is only a 5% variation, and that would be much better. So going back to Ohm's law. Ohm's law states that the current is directly proportional to the potential difference, providing the temperature of the conductor remains constant. And shortly you'll see why the temperature is important in this statement. But in general, he's just saying that, and he being Ohm, saying that the current is directly proportional to the potential difference. So remember the little squiggly symbol here is the proportionality. So I is proportional to V. And we use the equation, which is generally what we define as Ohm's law, of this V equals IR, or R equals V on I, or you could rearrange it as well and you could have I equals V on R. They're all exactly the same. V equals IR is probably the most common format that you'll see for Ohm's law. It's easy to remember. It kind of flows off the tongue. V equals IR. This tells you that the voltage, the potential difference, is equal to the current times the resistance. And hopefully you can remember from proportionalities, that tells you that V is directly proportional to I, which we just said. But V is also directly proportional to the resistance as well, provided that I is constant. So that is Ohm's law. It's really just an equation. We can use it to find the voltage if we know the current and the resistance. If we know the current and the voltage, we can find the resistance, and so on and so forth. So it's just using two known values to find a third unknown value. But it's very, very useful in electric circuits. Sometimes you'll see these ARV style triangles. And this is where I said in the last lesson that sometimes they'll switch out the I and the A. So I've called it an ARV, when technically it should be sort of an IRV or a VIR equation. But again, as long as you remember that the A is interchangeable with the I, because A is amps, it's the actual unit, but current is the symbol I. So what this is saying is that the voltage is equal to the current times the resistance. So if you put a little times here, it kind of gives you the equation. And you can rearrange it. So the voltage divided by the resistance equals current, which we saw in the previous slide as well. If we flick back real quick, you can see voltage divided by current is R, voltage divided by current is R, I times R is V, so I times R is V. So it gives you those sort of combinations. So if you're not super confident at just rearranging an equation like this, if you remember the VIR triangle, it basically gives you all of those combinations a little bit quicker without potentially needing to rearrange an equation. And this is for calculating watts, so we won't really deal with this a huge amount, but this is the same equivalent to tell you that the watts, which is the power, is equal to the current times the voltage. And I can do the same thing. The power, the watts divided by the voltage, gives me the current. Watts divided by amps gives me the potential or the voltage. So it's quite useful to have these VIR, WAV triangles, and you can come up with some good little acronyms to remember it. So WAV, VAR, there are some really good ways to remember those if you prefer this format to just having the equation and rearranging it. So time to use some practice with this Ohm's law. Here we've got a current flowing through a circuit, you're given the potential difference, and you want to find the resistance. So you want R, you know A or I, and you know V. It's just a case of using Ohm's law. In this case, you're given the resistance, you want to calculate the current when you know the potential, and then lastly, determine number of electrons passing through a conductor in half a minute. So that's very similar to the question we saw in the last video. So pause the video now, have a go at these questions. Okay, hopefully you've had a go at this. Let's look at some answers. So the first one, you rearrange the VIR, so resistance is equal to V over I. 12 divided by 0.235, because that was amps, so it's already SI units, Plug it in, 51.1 ohms. So again, remember we had 3 sig figs in this case, so our answer should be 3 sig figs. And ohms is the unit. Coil of wire, we're using exactly the same equation, R equals V on I. We had 22 ohms and 6 volts, so it's the same plug and chug. 0.27 because we had 2 sig figs in this case. And lastly, really the only trip here was that it was half a minute. So you needed to just convert that to 30 seconds. So this was using the Q equals IT, so the charge is equal to the current times the time. Or you could maybe have done it a little bit differently if you just thought about, well, how many electrons passing a point? If I know that amps is current per time, you could potentially use it that way. Sorry, charge per unit time. You could potentially use it that way as well. So we've got number of electrons is the total charge divided by the charge of one electron. Once we know the charge, we plug it in and we get our value. Number of electrons is 5.1 times 10 to the 19 electrons flowing through in 30 seconds. Ohmic and non-ohmic resistors. It's really important, and this links back to what I mentioned in Ohm's law about why it talked about the temperature being the same for that resistor or for that circuit. So in a nutshell, if a resistor follows Ohm's law, it is said to be an ohmic resistor. So if the current and the voltage are directly proportional, we say it's ohmic. As in ohmic meaning follows Ohm's law. In general, the resistance will actually vary with the temperature. So as things increase in temperature, the resistance increases, because if something's hotter, the particles are more spread out, it's harder for those electrons to flow, etc. Resistance will increase. Conversely, if something is very cold, its resistance will decrease. And this is why when you see things like superconductors and magnetic trains and stuff like that, they supercool these substances. So they put them in liquid nitrogen, or they do like liquid helium sometimes, helium cooling systems. They need these circuits very, very cold in order for the resistance to be so low that we can produce these sort of super levitation effects. So that's why the temperature is important there. So if we have a resistor that is not following Ohm's law, so if we graph the resistance, if we graph the current compared to the voltage, we find that it is not linear. So in this case, we've increased the voltage across a circuit, but the current is not increasing consistently. It starts to sort of drop off a bit. That tells you that resistance is actually increasing over this point here. As the temperature gets hotter, it starts to increase its resistance. So we say that is non-ohmic. So a real common example is something like a filament globe, an incandescent light that uses the little sort of coiled wire to heat up, those kind of things. Because when you first turn them on, they are colder, so they'll actually be a little bit more bright. And then as they sort of warm up, they get hotter, the resistance increases. They'll have more resistance, less current flowing through them. They'll get a little bit dimmer. In most cases, you can't even see this, but you can measure it. And we'll do this when we do an Ohm's law experiment next lesson. So this is that typical graph that you'll see. So you may be asked to draw a current versus potential graph for a non-ohmic resistor. The key is you just need to know that it's not a linear relationship, so it speeds off towards that sort of exponentially kind of trend. So ohmic follows Ohm's law, doesn't change with temperature. Non-ohmic is really, for most cases, the real world, doesn't follow Ohm's law perfectly because the temperature changes with, the resistance changes with temperature. So now we're looking at resistivity and how that links to resistance. If a charge flows through a conductor, the resistance applied to it depends on several factors. So we've seen that certain things can affect resistance, and the resistance is restriction on the flow or the current of a circuit. So the length of the material is going to affect it. Obviously, the further you've got to travel, the more resistance is going to build up in the circuit over time. The area of the cross-section, so if you cut the wire and look at it, how big is it? What is the cross-sectional area of that wire? So the fatter the wire, the less resistance we're going to have. The type of material, because if we have a highly conductive material, the resistivity and the resistance is going to be much less than if we have a very poor conducting material. And the temperature, as we just saw, the temperature affects the resistance of a circuit. So looking at the length of the material. Resistance is directly proportional to the length of a conductor. So resistance, capital R, directly proportional to the length. You could, I guess, use D for distance here, but just to be clearer that we're talking about wires and resistivity, we use capital L to signify that. So directly proportional to the length of a conductor. This is because if you think about it at that atomic level, the electrons are going to have twice as many collisions along the way as they're trying to travel. And every time they bump into something, they slow down, they lose a little bit of energy. So that's going to be a linear relationship. For the same material, it makes sense that it's going to hit twice as much stuff over twice the distance. For the cross-sectional area, resistance is inversely proportional. And hopefully this kind of makes sense, because if you've got a much bigger object, there's a lot more space for the thing to get through. There's a lot less collisions within that conductor. So it's just like having a really big hose, and it's very easy for an object to pass through a really big hose compared to a really small hose where they're going to bump into each other and it's really crowded. It's like trying to fit all of the students down a really narrow hallway in the break time versus we have a really big hallway, heaps of space we can all flow through nice and easy. The type of material has a property called its resistivity. So every material has a resistivity value, and we use the Greek symbol rho, which again, just to be confusing, is the same symbol that we use in density. So Greek symbol rho is also resistivity, and it's the resistance of a 1 meter length of wire with a cross-sectional area of 1 meter squared, which is huge. Think about it, it's a meter long, but the cross-sectional area is 1 meter squared, so that's massive. Resistance is directly proportional to the resistivity of a conductor. And that kind of makes sense. If you double the resistivity, you've doubled how much resistance per meter for 1 square meter diameter object. You would expect the resistance to be affected by the same amount. And lastly, temperature. It's just a measure of the kinetic energy of the particles. So if you go back to our particle theory from earlier sciences, a high temperature means a lot of kinetic energy. It's vibrating a lot. So if you have that, then you've got more kinetic energy, which means they're going to collide more often. They're going to hit with more force. Then they're going to lose energy much faster. Whereas if they're just sort of slowly creeping their way through, they're not going to collide nearly as often. They're not going to hit with nearly as much force. So the resistance is less. So this is why when we talked about those non-ohmic resistors, the temperature affects it at sort of an atomic level. So this is the resistivity equation. Capital R, which is the total resistance, is equal to rho, the resistance of, or the resistivity of that material, the length of the wire in meters, and A is the cross-sectional area. So don't confuse A with amps, and rho is resistivity, not density. So resistance, that stayed the same, thankfully. Resistivity, length in meters, area. Time to practice it. So we've got a copper wire, which has a resistivity of 1.7 times 10 to the negative 8 ohm meters. Calculate the resistance of a 2 meter length of wire that has a diameter of 2 millimeters. So use that equation. You're going to need to find what the cross-sectional area is, plug it into your value. Then you've got the 50 centimeter wire, you know its radius, you know its total resistance. You want to find what is the resistivity of that material that the wire is made of. And lastly, if the resistance of a wire is R, state the new resistance in terms of R if the cross-sectional area decreases by a factor of 4. So this is kind of like one of those equations where we've seen before the SACE language uses things like state or show that the resistance would be this. You don't actually need to make any calculations. This is just justifying using proportionality. So pause the video here, have a go at those questions, and I'll give you the answers shortly. Alright, time for some answers. In question 1, we're plugging in the equation. A, our cross-sectional area, because it's a circle or it's a cylinder, it's pi r squared for the cross-sectional area. Plug all that in, we get our values. 1.1 times 10 to the negative 2 ohms is our resistance for that circuit or that piece of wire over 2 meters. Number 2, again, exactly the same equation, plugging everything in. We've got the radius of 3 mils, so we needed to calculate the pi r squared for it. We knew that, we had to just rearrange. The resistivity is 2.3 times 10 to the minus 4 ohm meters. So that is ohms every meter. If the resistance of a wire is R, state the new resistance. This was that proportionality that I was talking about. So here they wanted something like to say that R is inversely proportional to 1 over A, or you could say it's directly proportional to 1 over A. The resistance will be 4 times larger if the cross-sectional area decreases by 4. So if cross-sectional area decreases, if this number gets 4 times smaller, then this value gets bigger. It kind of makes sense. You can look at it mathematically. If you double this, this gets smaller because you've increased the fraction. So if this was a half and you double it, it becomes a quarter. And a quarter is smaller than a half, so this is decreased by twice the amount. If you go the other way and you decrease this by 4, this will do the opposite. It'll increase by 4. So the new resistance is just 4R. From here, workbook questions start with resistance. So that's linked on the OneNote again. Page 79, question 1 to 6, and then have a go at some resistance and resistivity questions. So that's the page 82, question 1 to 5, just to link it up. Answers are at the back of those documents, so if you want to check your work, if there's anything you're not sure about, please let me know. It's really important that you get your head around these sort of concepts so that we can expand on it in future lessons.